In this lecture, I will be talking about the principle of superposition in electric circuits. This is a very powerful principle that's used widely in engineering and physics, and it goes something like this. So imagine we have a circuit and we want to calculate a current through it, IR1. And using the principle of superposition, we can simplify the analysis by creating simpler circuits to analyze and then combining the results instead of doing, say, something like a nodal analysis or mesh current analysis directly on this circuit. And the idea behind it is that for a linear system, and the definition of a linear system is beyond the scope of this course, but for a linear system, the total response is the sum of the responses of the independent sources acting individually. So that means we'll only look at the circuit with one independent source active at a time, calculate, say, the response, so let's say the IR1, and then repeat for every other independent source. So I'll go over the steps of the method, and then I will give a simple example to show how it all comes together. So the first step is that we let only one independent source be active at a time, and the important thing that we're only working with one independent source at a time. And remember, the independent sources are the ones with the circles, a voltage source or a current source. So then, the second step is that we zero all the other independent sources. Important thing is we zero the other independent sources. And what does that look like? Well, how about for a voltage source? If we zero it, that means we make its value 0 volts, and just exactly the same as the shortcut method for finding the Thevenin resistance, a zeroed voltage source becomes a wire or a short circuit. Then, if we zero a current source, then we're making its value into 0 amps, and that becomes an open circuit. So this is just like the how to find R Thevenin with the shortcut method. So then, the third step is that we always keep the dependent sources for all of the responses. So every time we repeat this more simplified circuit analysis, we always keep the dependent sources present. So we always keep them, and the dependent sources are of course the ones that are denoted by diamonds, so it can be a voltage source or a current source. The next step is to determine the response, and we'll call it R prime. That's what we're denoting it as. And so in the example above, it would have been IR1 prime. And this prime doesn't indicate a derivative. It indicates just the response that we're working with. And so we determine the response at the desired location in the circuit. So let's say IR1. And in this course, the response will be either a voltage or a current. The fifth step is to repeat all these steps for all of the independent sources, and then we determine the subsequent responses, and we'll denote them R double prime, R triple prime, etc. So we'll have a response for every independent source. And then we sum all of the responses, and that is a simple arithmetic sum. So R equal to R prime plus R double prime, etc. And so R is the total response. So if we were finding that IR1, that would be the final result, and we get that from the individual responses from the application of superposition, and we have one individual response for every independent source. And it's important to note that you cannot use superposition to solve for power directly because power is nonlinear. And just as a reminder, these R's in our course are going to be currents or voltages. So let's look at our example to see what this analysis using superposition looks like. So we're going to find IR1 using superposition, and we note that there are two independent sources, so we have two responses to calculate. So what we're going to do is we're going to do the first response, and that looks like this. We're going to find I prime R1, so this is the first response, and so we denote it with a different label, I prime IR1, and we're going to be using the independent current source as our first active source, and we zero all the other independent sources, and in this case we just have one other independent source, and that's our VA voltage source, and we're denoting it with a wire because when we zero a voltage source, it becomes a wire or a short circuit. So we've drawn a wire in its place, and we've just put some red dots to denote that that's where it was. It's just to help us keep track of things, and it's a short circuit. And note that we keep the dependent voltage source in the circuit. We keep it for all of the responses. And then we use circuit analysis to find I prime R1. So this is a more simplified circuit than our original. And then once we calculate I prime R1, then we go to the next response, and that is going to look like this. So we're going to find now I double prime R1, and this time the voltage source is active, and we've zeroed the current source, and when we zero a current source, it becomes an open circuit, so it's out of the circuit. And we've just denoted it with dots where it was, and it's an open circuit. And then we repeat a circuit analysis and find I double prime R1. And note that we are keeping the dependent voltage source in the circuit for this analysis as well. So then, when we find the two quantities, the two responses, we add them up. So IR1 is going to be equal to I prime R1 plus I double prime R1. And so IR1 is the total response. So that's for the original circuit. And so that we would get the same quantity as if we applied some sort of analysis like nodal or mesh to find IR1 in the original circuit. We get the same value. And the total response is comprised of the sum of the individual responses on the right-hand side. Okay, so that is the method for using superposition. So now, just out of curiosity, just so we can understand this a little bit better, what if we wanted to know the power in R1? So we have R1, let's say that value is given, let's say it's like 10 ohms or some sort of thing like this, and we've calculated IR1, okay, using superposition. So that's a total response, IR1. So then we can find power using a formula that we know where power is I squared R. So it would be the power of R1 is the current through it, IR1 squared, times R1. Okay, it's pretty straightforward. And then if we substitute for the responses that made up the total response, then it would be I prime R1 plus I double prime R1 all squared times R1. But let's say we tried to use superposition directly. What could that look like? Well, then we might think, okay, we can just find the powers individually. So we might say, oh, I prime R1 squared times R1 plus I double prime R1 squared times R1. And is that the power? Is that correct? So then let's break it down a little bit. Let's go back to our original where we had I1 prime R1 plus I double prime R1 squared times R1. And if we expand that out, we get the term above in red. Okay, so it's looking a little bit more complicated. So let's compare the two expressions for PR1. So one way, if we used, on the left-hand side, if we used superposition directly, we have the expression as shown, but we see that it's not equal to the expression on the right because we have an extra term. So this term is present in the correct solution. So this is demonstrating that we cannot use superposition to find the power directly. So power is nonlinear, so we cannot use superposition to solve for it. We will only use superposition to solve for current or voltage in this course. So if we wanted to solve for the power using superposition, then after we use superposition to solve for the current or voltage, then we can solve for the power if necessary. But in this case, we would use the total response to solve for the power. So that's after we complete our superposition analysis and find the current or voltage, and then we can calculate for power. Okay? That concludes the lecture on superposition, and I will give some examples applying it.